Hello and welcome. We're returning to further maths for the harder definite integral. It's the integral from 0 to 1. The log of, the argument of the log is the square root of x plus the square root of x plus 1. Is this hard? Well, the question is, it can be hard if you don't spot certain things. I mean, the natural things that goes through your head when you look at something like this, you split the log, the plus doesn't actually help, so that is a problem. The next thing is to think about substitutions, and the substitutions, of course, you think of the square root of x possibly, but the problem is then you cannot really, if you use u is equal to the square root of x, we got a problem with this quantity here. And this is actually a lot easier if you spot something. And the something to spot is that logarithmic form of the r shine of x, which is, of course, the log of x plus the square root of x squared plus 1. Further maths, normal further maths, nothing, no further maths. And if you look at this expression and you replace x for the square root of x, well, quite clearly, this log becomes, you're replacing x for the square root of x, so it becomes as x plus 1. So that is nothing more than the r shine of the square root of x with its limits. And of course, it'll be interesting if some of you can actually attempt it and go directly for a substitution. For example, if you put there x is equal to shine squared, does it work just as good? You can also try, pardon me, a trigonometric substitution even. X is equal to the tan squared. So you get 1 plus tan squared to extract some kind of sec. But at the moment, I'm more than happy to proceed with that. And what I'm going to do is I'm going to use, this is the shop I'm opening there. I'm going to use a substitution and I'm going to call theta the whole thing. Because as I see these things, the arc trig and the r hyperbolics, I see them as angles, so I always call them theta. Theta is the r shine of the square root of x. The shine of theta is equal to the square root of x. X is shine squared of theta, and my dx is, of course, 2 shine theta cos theta, and the limits 0 and 1. 0 maps to 0. The r shine of 0 is 0, and 1 is the r shine of 1, which I can call alpha. I'm inclined for this question to work this without limits. Ignore limits, because it'll be easier to go probably back into x and then put 0 and 1 is going to be actually much easier. So forget about this. I have them there, but I'm not going to be writing these things in there. So at the moment, this is gone. This is a theta, and the dx is 2 shine theta cos theta d theta, which is an identity. It's not a good idea to switch this into exponentials and have theta with exponentials. The integration by parts is not going to be very pleasant. It's probably better to leave this as theta shine 2 theta. That's this identity, d theta, and you're still going to have 2 parts, but they're much nicer. Theta 1 shine 2 theta, a half cos 2 theta. And the integration, of course, is the product of that. So that's half theta cos 2 theta, the product of that integrated, minus the integral of a half, this diagonal here, cosh of 2 theta d theta. And this will now go into this quantity, minus 1/4 sine 2 theta plus a constant. So we really need to go back into x's, and the way back into x's is through sines. So I'm going to put a half theta. This is going to be 1, let me just write it, 1 plus 2 sine squared theta. I'm using the identity cos 2 theta is 1 minus 2, not sine, from the trig. And of course, by Osborne's rule, if I have a cosh, it will make that to a plus. And it's a good way for me to check that I haven't made any mistakes. So that's that bit there. Yeah, it is. So this I need to rub off in a minute. And that, of course, is, sine of 2 theta is 2 sine theta cos theta. If I have sines, it doesn't change. But the 2 that's going to be produced, I'm going to write it as a half sine theta cosh theta plus c. Okay, so now we're a lot better. Because we have sine theta is of course the r sine, that's okay. The cosh is not a problem because of course the cosh of theta is the positive square root. Remember, the cosh is always bigger than 1 of 1 plus sine squared theta. That's just merely using the identity, what you call it, cos squared plus sine squared is equal to 1 and nothing more for this. So if we change all of that, we have a half theta. So we'll leave it like that. Let's write it first of all. Plus 2. The integral is done now. We'll be putting the limits and we finish. Is minus a half sine theta, and the cosh is of course the square root of 1 plus sine squared theta plus a constant. And we're ready now to reverse into x and finally put the limits back in. And the limits, of course, are the original because we're going to go back into x, and therefore it's going to be 0 to 1. So just bear with me till I clean the tablet. So what do we have so far? Half theta. Half theta is half the r sine of half times the r sine of the square root of x. 1 plus sine squared is 1 plus x squared with a 2 there. Sine squared theta is x. So no, it's not. There's a mistake in there. Wait a second. Sine squared is just x. That's 1 plus 2x. That we've got in there. Okay, so far. And where are we going from there? Minus a half. The sine of theta is the square root of x. And 1 plus sine squared of theta is going to be another square root there, and that's 1 plus sine squared, which is another x plus c. And I can guess we can get into any kind of form. We have there a half. How can we write this this bit here now? is the question. We can, I guess, actually probably be a good idea to put the limits now. I think limits in, so that's going to be this quantity. And that's 1 plus 2x and minus a half. And if we multiply the third quantities, the radicals there, we get that. And 0 to 1. And where are we with this now? Notice that the bottom limit will give us 0. This will be 0 when we put 0. And this will be 0 from the r shine of the square root of x. So the only contribution will be from the top one. The r shine of the square root of x is, of course, 1. So that's the half r shine of 1 times 3. That's from 2 times 1 plus 1 times 3 minus a half. And what do we have there? Minus a half root 2. And we could, I guess, write it as 3 over 2. That's this quantity here. We can write this in log form if you prefer it. 1 plus square root of 2. That's the r shine of 1 logarithmic form. Minus a half root 2, or equivalent statement. It doesn't actually say how to write this particular question, but I think that is good enough in this particular case, and we can leave it like this. Okay, I hope you followed this one, and as I said in the beginning, it'll be interesting to see some comments about how different people approach this particular one, whether they went for slightly different substitutions in the beginning. My brain was just locked into seeing this R shine, and I couldn't get away from anything else, so I didn't really try it. Okay, I'm signing out for the time being. I'll see you real soon with more stuff and more maths. See you soon. Bye-bye.